Okay, everybody, here we go. I'll just say if I mess up here, I'm not going to edit the video. Hopefully I catch any mistakes I make, but that's your job to let me know in class, right? But I assume, yeah, that it's possible I might make a mistake, and hopefully I catch it, but you'll see it, and because this is not edited. So, here we go. Number one, a recent study of 15 ninth graders. The mean number of hours per week they played video games was 16. We're assuming that the distribution is normal, and we want to determine the following. What is the best point estimate of the population mean? The best point estimate of a mean for the population is the sample mean. It is unbiased because the expected value of the sample mean is the mean for the population. So for this particular problem, the best point estimate is x bar. X bar in the problem turned out to be 16. Part B, we want a 95% confidence interval for the mean time students are playing video games. We are given sigma is equal to 3.0. So we want a confidence interval. We are told what the population standard deviation is, and so therefore we have a formula. In that particular formula, I'll write, I guess, right here, x bar plus or minus. We're going to work with a z because we have the population standard deviation, sigma divided by the square root of n. Alright, so basically what we're doing here, I'll draw a little chart. We have the sample mean, and we want an interval such that there's a 95% chance the actual true mean for this the population is between these 2 points. And since we are given the population standard deviation, we're going to work with the z-table. Now, so if you go to your z-table somewhere, there it is. You have this little chart, or somewhere you have this chart. For a 95% confidence interval, z is taken to be 1.96. So, in this problem, we know that z is equal to 1.96. Sigma is given. X bar is given to be 16. And then n is equal to 15. So we plug these values into the formula, and notice that we get z times sigma divided by the square root of n. Turns out to be, you can do the math, rounded to 2 places, 1.52. So I'm going to add 1.52 to x bar. I'm going to subtract 1.52 from x bar. And you can show yourself the interval is 14.48, 17.52. This is the interval that we expect with a 95% confidence that the actual true amount of time on average students are playing is somewhere between these two numbers here. So I'll just point out, first, you're looking for a confidence interval. Second, you're given the population mean. That tells you you're going to be working with the z distribution, correct? All right, moving on. Similar problem, working with the above information, but in this particular case, we want a 99% confidence interval. The second thing we want to note is that we're not given the population standard deviation. In this one, we're given the sample standard deviation. The only difference here is our formula is going to look like x bar plus or minus t times s divided by the square root of n. So we're going to have to find the t value associated with a 99% confidence interval. We're going to be working with the t-table. So if we work with the t-table, we have an additional calculation, and that is the degrees of freedom. And it's always one less than the sample size. So the sample size is 15. 15 minus 1 is 14. So I'm going to look for a 99% confidence interval. Degrees of freedom is 14, and I have to work with the t-table. So I'll go down to my t-table. Should be at the bottom. Okay. We're looking for a 99% confidence interval, so that's right here, very last column. And we want the degrees of freedom to be 14. So if I look for row 14, there I am. If you move over to last column, we see that the t-value is 2.977. So our t-value here is 2.977. Again, x bar is 16. S is equal to 2. And n is equal to 15. And so therefore, I'm going to calculate t times s divided by the square root of n. Again, I'll just mention n is equal to 15 here. And then s came from the problem, right? 2.0. If you do the math, you will get this here is equal to 1.54. Okay, rounded to 2 places. And so therefore, for the confidence interval, I will be adding 1.54 to 16, and I will be subtracting 1.54 from 16. And when I do that, the lower number is 14.46, the upper number is 17.54, and so I have a 99% confidence that the actual true mean is in this particular interval. Okay? Now, for number 2, I really did not discuss in class, at least I don't think I did. This depends on what class I'm teaching. But number 2 is a little bit slightly different, so I'm going to explain a little bit more. The formulas are in my notes. We have a sample of college students that own cars, and we reveal that out of 120 cars, so we took a sample, and that sample was 120. We found out that 24 had a manual transmission. 24 of them had a manual transmission. We want a confidence interval that the true proportion, now this is what we haven't discussed, at least I don't think so in class, the true proportion of cars. What is a confidence interval for the true proportion of cars? Well, you know what a proportion is, right? A proportion, and since we're working with a sample, if you recall we did this early in the semester, we represented the sample proportion by p hat, and the sample proportion is just how many divided by the total possible number. 24 had a transmission that was manual. We had 120 in our sample, so that proportion was equal to 0.2. That tells us Q, which represents the opposite, would have to be 1 minus 0.2. which is 0.8. So 20% of our students in the sample had manual transmission, 80% did not. And we're trying to find a confidence interval where we are 90% confident that the true proportion of students that own a manual transmission car is in this particular interval. Now, here I'll just mention that since we're working with a sample, this is one thing you don't know, that the sample deviation is given by the square root of p hat times q hat divided by n. If you do the math and type in, I'll enter 0.2 for p hat, 0.8 for q, and then n here is 120, you are going to come out with s equal to, let's see, hold on, let me check to make sure. Okay, I had to do the math here. So anyway, continuing on, if you do your calculation here, rounded, you're going to get s is equal to 0.0365. Okay? 0.06365. That's rounded to 4 places, all right? So therefore, this is what the confidence interval is going to be. You're going to be adding to p hat plus or minus t times the square root of p hat q hat divided by the square root of n. That's what you're going to be multiplying by. Now, the book might show you z, but this is really a sample. There's a reason why. But anyway, this is really a sample, so I want to kind of be consistent, because when you're working with a sample standard deviation, you typically go to the t-table, okay? But we're going to find out that, notice that our sample size n is equal to 120. And so the degrees of freedom is equal to 119. When you go to the table and you look at the degrees of freedom, as I mentioned in class, you're all the way at the bottom, infinity, right? And so therefore, I need to just work with this row here, but this row here is actually z-scores. So for a 90% confidence interval, it should be this one right here, yeah, okay? It's 1.645. So we know t here is 1.645. If I multiply this by 0.0365, p hat plus or minus this is 0.02 plus or minus 0.0601. Okay? So when I subtract 0.06, I get a negative number, but we're talking proportions here. So the smallest a proportion can be 0. So I'm going to have to start my interval at 0 because, again, subtracting off this, I get a negative number. Context of the problem just tells you it can't be less than 0. If I add it, I get 0.0801. So here's a confidence interval that the true proportion for this population is somewhere between 0 and close to 8%. So again, this is just an additional formula. It's in the notes. Really nothing changes much here except what you're looking for. A confidence interval for a proportion. So it's this formula. You're going to be working with the t-table, but technically it's going to be the z-table. And that's why the book, because the sample size is always pretty large for a proportion. And your t-table is always going to be the very bottom row for degrees of freedom, which is the z-table. Okay? So anyway, going on to the next problem, number 3. Number 3, we're looking at hypothesis testing. And so if we look at this problem, nationally the average cost of building a home is $117 per square foot. We're going to take a random sample of 20 new homes in the South that indicated the mean cost was $125 with a sample standard deviation of 20. Step 1 of the hypothesis testing is to determine what the hypotheses are. So we want to test the claim that the true mean is higher in the South, and our testing level is 0.10. I'll explain that when we get to the chart. So the null hypothesis is basically nothing changes. So the null hypothesis is the mean is 117. We are claiming it increases. We're claiming that mu is going to be greater than 117. Okay, so that's our hypothesis. So the critical region depends upon the alternative hypothesis. Well, if you think about it, we are going to reject the claim that it stays the same in favor of the alternative hypothesis if we are substantially larger than the mean. That is, at some point out here, okay, if there's any indication that we're way out here, we're going to reject the null hypothesis. All right, so this is what we need to do. We have to come up with the critical region and then generate a test value. Well, since we are working with a sample, okay, deviation, we are going to be working with the t-table. And so from the problem, we know that S is equal to 20, N is equal to 20. Since we're working with S, we need a t value degrees of freedom is going to be 19. The region over here is alpha, which alpha is taken to be 0.10. 10% of my data is over here. That's kind of what it's saying. All right. So now I'm going to go to the t-table to determine what the critical region is going to be. The critical point, I like to call this. So going to the t-table. Now, if you look at the top of the t-table, this is a one-tail test, meaning we only have one side. We're working with alpha equal to 0.10. So since we're working with one side, we're going to be working down the second column here. A one-tail test, alpha is 0.10. Our degrees of freedom is 19. So if I go down here, my degrees of freedom tells me the t-value is 1.328. You see that? One-tail test. 0.10 is the level of confidence, the level of significance, sorry about that, level of significance. I go down here, 1.328. So therefore, what I know is now that if when I calculate my test value, if it ends up in this region here, I'm going to reject the null hypothesis. So what is the test value? Again, the test value formula is going to be x bar minus the mean of the null hypothesis divided by, well, again, I don't know what the population standard deviation is, so that's going to be S here, and then the square root of n right here. So getting my information from the table, not the table, from the problem, we know that x bar is 125. The null hypothesis mean is 117. S is 20. Divide that by the square root of n, which is 20. If you do your calculations, you should come up with 1.78899. Now, when I go look at my critical region, 1.7889 is somewhere over here because it's above 1.328. This is the region of rejection, and so therefore I am going to reject the null hypothesis. The null hypothesis at a level of 0.10, level of significance. That's really the probability of making a type 1 error. That is, there's a 10% chance, okay, I rejected the null hypothesis when it was actually true. Okay, I'm going to move on to the next one. Now, it's the same problem, except we're going to test the claim that the true mean is actually lower in the south, and the level of significance is 0.05. So once again, the null hypothesis is always nothing has changed, so 117. The alternative hypothesis is what you're claiming. We are claiming now that the mean is lower. That is, the mean is going to be less than 117. We do not put the sample mean is nowhere up here. This is always the assumed status quo of what's happening in the population. All right? All right, so now we're assuming that the mean is actually decreased. So if the mean is decreased to such a lower number in our sample, we're going to be rejecting. So our mean mu is 117 here. There's some point at which we're going to want to reject. In this problem again, the sample standard deviation is 20. Our degrees of freedom is equal to 19. And our sample size, our sample mean is 110. So again, this is not edited, okay? All right, so now I'm going to look up the t-score or the t-value associated with this. Going to my t-table. In this problem here, it's a one-tailed test, but we're working at a level of significance of 0.05, so we're going to be working down the third column, right here. Degrees of freedom is 19, so in this case here, t is going to be 1.729. So, since we're on the left side, this is going to be a negative 1.729. That's the only thing we have to keep in mind. Remember, right side is positive, left side is negative, right? So, we're going to be working over here, negative 1.729. We go calculate our test score now, and our test score or test value is going to be, again, the sample mean minus the assumed mean divided by 20 divided by the square root of 20. When you do the calculation, you get negative 1.565. If you look at a little graph, the critical region, our data value is going to be somewhere here. That is not in the critical region, so we do not reject the null hypothesis. So, do not reject the null hypothesis, okay? All right, moving on to the last problem. In our last problem, we have the Bright Lights Manufacturing Company has light bulbs that on average last 1,100 hours. The standard deviation is 200. We now take a sample of 35 light bulbs. We come up with a mean average life of 200. We want to test the claim that the true mean has changed at a level of 0.5. That is, the level of significance is 0.05. What are our hypotheses? Null hypothesis, nothing's changed, so mu is equal to 1,100 hours. Alternative hypothesis, the true mean is changed. Something's different. We don't care if it's higher or lower. It's just not equal to 1,100. What is our critical region going to look like? Well, this is a two-tailed test because, again, we don't care if we're above or below. As long as we're far enough away, we're going to reject the null hypothesis. Now, in this problem here, we're given the population standard deviation of 200. So we're going to be working with z-scores. X bar is equal to 1,200. N is equal to 35. So going to our z table, well, let's just look at this. There's 0.05 amount of data outside of these two bars here, right? So that tells us there's 95% in the middle. Since we know the population standard deviation, that tells us we can really just work with our z-scores and the confidence interval z-values, which I'm trying to get up to. There it is. 95% confidence interval 1.96. That tells me that this z-value is 1.96, and so this is a negative 1.96. Okay? Again, we're working with a z-table. I need 5% of my data to be on the outside. That tells me 95% of the data is in between. Okay? I'll look up it in the z-table. Z is 1.96, so the negative value over here is minus 1.96. The test value in this situation is going to be x bar minus the null hypothesis mean divided by sigma over the square root of n. You can plug this in. X bar, null hypothesis 1,100, sigma 200, n equal to 35, and you come out with 2.958. 2.958. If you look up here, 2.958 is out here somewhere. That's the region of rejection. We are going to reject the null hypothesis at a level of 0.05%, meaning, again, we're going to say something has changed. And we're 95% sure that has changed, but there's a 5% chance we made a type 1 error. Anyway, I'm going to just mention and point out that in the case, this is not on your paper though, I just want to point out that if you go and calculate x bar equal to 1160, you can show that the test value, again, this is separate from the problem, just to give you a little bit more extra practice, that if you calculate x bar, you're going to come up with a test value that's going to be equal to 1.775. In that particular case, that is going to be in the non-rejection region, so you would not be rejecting the null hypothesis. If you go out and find out that the x bar turns out to be 1030, and you go through your calculations here, your test value is going to turn out to be negative 2.071, and negative 2.071 is over here, which is a region of rejection, so you would reject. So I'm just kind of showing you, if you want a little bit extra practice, plugging things in. If it were the case x bar was 1160, you wouldn't reject. If it were the case x bar came out to be 1030, you would reject. Would not reject, you would reject. Okay? Alright, so I hope this helps a bit. I know I kind of said a few things, but again, this is unedited. Use it or don't use it. Okay?